So the last piece of the puzzle in our discussion about ordering of results in Java parallel streams will focus on the ordering of results based on the operations that are performed. If you recall earlier, we talked about the ordering of results based on the input source, the collections that were used, for example. Now we're going to talk about operations that affect results order that are intermediate operations or terminal operations. And we'll take a look at a bunch of different examples, all of which you can find here in the EX21 folder again. So certain intermediate operations will affect the behavior with respect to ordering. So here are some examples, and some of these are pretty obvious, like sorted. Well, that's clearly going to affect the ordering because it's going to sort things. But other ones may not be as clear. So limit, skip, unordered, those are also operations that can affect the ordering of things, whether if you skip over stuff, for example, or whether if you can actually explicitly say, I don't care about the order, that will affect the results. Or I'm going to limit things to only the first n elements and so on. So let's take a look at an example, keeping in mind again that ordering and sorting are not the same thing. So here we've got ourselves the same example we did before. We've got an array, 2, 3, 1, 4, 2. We turn that into a list. And then we're going to say list parallel stream. And then we're going to do a bunch of other stuff. So keep in mind, first of all, that to start out with, it's in a list. And a list is going to allow duplicates so the values can be non-unique. But the first thing that we do here in this stream is we say, I only want distinct elements. So, of course, that's a stateful operation. Why is it a stateful operation? Because it's got to basically queue up all the elements to figure out which ones are duplicates. So once it gets done queuing them all up, it'll then say, OK, now I'm going to take out the ones that are duplicates. I'll only allow one of each thing. So that's a stateful intermediate operation. And then we're also going to limit things. So we're only going to let the processing go up to a certain limit, which is particularly complicated in parallel programming, because remember that we've got to do two things which seem in conflict at some level. We have to allow non-deterministic ordering of intermediate operations, but we have to stop as soon as we've hit our limit. And limit is something that is really a sequential concept, if you think about it. So this is why, FYI, using limit with parallel streams is a bit perilous, because it's going to have extra overhead. It works, but it's going to require more coordination. And in fact, that's a good example of, stateful mutable data being the root of all evil. Somewhere in the intermediate stages, the internals of Java parallel streams, when it sees limit in a parallel stream, it's got to have some state to keep track of how many items have been seen and the order that they've been seen. So you're actually basically kind of serializing the processing. Not that it works, it just isn't as efficient as you might want. In this particular case, the result has to be 4 and 8 because we are going to not allow duplicates, so this other 2 gets dropped off. And we're going to limit ourselves. That, of course, assumes that we can, we don't limit ourselves where S output limit is not like, 2 or something like that, in which case we wouldn't get that result at all. However, because we use limit and because we use distinct, and those are stateful operations, then the code will run slower, even though the ordering will still be preserved. And this kind of comes back to our earlier discussion about how do things get ordered. So this is the earlier discussion on steroids, because now we're not only insisting on ordering, but we're also insisting on these other semantics that are stateful, like distinct and limit. So the key point about this is that streams gives you lots of powerful capabilities that are largely orthogonal semantically. In other words, you can take a sequential stream and make it distinct. You can take a parallel stream, make it distinct. You can take a sequential stream and you can limit it. You can take a parallel stream, you can limit it. You'll always get the same results. It's just that you may slow things down appreciably because of the semantics that are required to preserve those requirements. So here's something else you could do if you were so inclined. You could say, I really don't care about the order in which the results are going to be presented. And so I'm going to explicitly say, even though this is an ordered collection, because a list is an ordered collection, I'm going to tell my stream, I don't care. And so in that case, you could process this in a way that would have less overhead with respect to the final results. Now, there still could be overhead from using distinct and limit, but you don't have to worry about ordering the results. And the best way to figure out what makes a difference is to take the example code I have in my EX21 folder and run it and give a large N for the runs, so you can actually see the results and how the differences in semantics make a difference in terms of the performance that we see. So if we put unordered here, then the output could either be 8.4 or 4.8. We don't know, we don't care, because we said we don't care because we made this thing unordered, even though it starts from an ordered collection. There are also terminal operations that affect order. These were the intermediate operations we just looked at. There's also terminal operations that affect ordering as well. So here's a good example, the for each ordered method. So for each ordered will ensure that encounter order is maintained. So in this particular case, we have something similar to what we did before, except rather than using toArray as a terminal operator, we're just going to go ahead and add each element into this array list. Now this is funky for all kinds of interesting reasons. This particular example uses an unsynchronized array list. This is just the one you get out of the box. There's no support for synchronization. If multiple threads were simultaneously trying to insert and or remove elements into this list from different threads, chaos and insanity would ensue. However, the way that for each ordered works, it actually grabs a lock and it checks carefully before it does the method reference, in this case the add operation, such that the caches are properly flushed, so there's no memory inconsistencies, there's no race conditions. So even though we're using an unsynchronized data structure, for each ordered actually has implicit synchronization. So that's good in the sense we don't have to know or care about this. It's bad in the fact that it may be slower than we would expect because we're forcing synchronization to occur. So you typically don't want to use for each ordered unless you really, really, really care that the results come in encounter order. I would almost go as far as to say you should never use for each ordered. There's a handful of cases where it comes in handy, but you're almost always better off doing something else, like using collect or something instead. In contrast, this example could use for each instead of for each ordered, but in that case, you have to replace the type of the results data structure, this local variable results, so that it's no longer an unsynchronized data structure like array list, but instead is a synchronized data structure like concurrent linked queue. Now, what you're really doing here in some sense is you're robbing Peter to pay Paul, right? So the for each ordered that we saw over here didn't require us to use a synchronized data structure, but it put synchronization in the terminal operation. Over here, we no longer have synchronization in the terminal operation, but now we're using a synchronized collection, which will also have it'll acquire and release a synchronizer to make sure that we don't corrupt the internal data structure. So if you were to run this code, you would probably find out it performs roughly the same because there's locks taking place in both areas. A far better way to do things, let's see, I don't really show that here, but a far better way to do this would be to use something like collect or toArray, which is designed to work properly without requiring extra synchronization because of the way that the internal data structures behave in a tree-like fashion that never tries to merge things in multiple threads. They always merge things into one thread in a very careful, clever way. So if you're going to go with the for each method with a parallel stream, if you're so inclined to punish yourself, which you probably shouldn't do, at least make sure you use a collection that supports thread-safe insertions and removals. Okay, so that's the end of our discussion of ordering. Now, this is a bit esoteric in some sense, and most of the time you probably don't know and don't care. And if you just stick with what you get out of the box, you'll usually be fine. But in cases where performance matters, be aware that using stateful operations on ordered collections and with parallel streams can give you extra overhead that you might not expect. So the lesson learned there is that parallelism is a subtle thing, and even though you can do it syntactically, and even though the results come back semantically, you may in fact not get a win from using parallel processing.